Now, where we left off was 1908, and that was Rutherford discovering that we had positively charged nucleuses. In 1913, a fellow by the name of Niels Bohr came along, and he developed a better model for the atom, which incorporated Rutherford's positively charged nucleus, with an electron kind of living in orbits out here. But it took it a step further, and it talked about how come we have discrete frequencies or discrete energy levels of atoms. So Niels Bohr came up with a model that's more familiar with what we know today, where we're going to have this electron, and it's going to live in the ground state. Now what we do is we very typically call this ground state n is equal to 1, and we might call the second state n is equal to 2, and we would call this n is equal to 3. Fellows by the name of Albert Einstein and Max Planck called these discrete quantized energy states or orbits, and we can draw this thing called the energy level diagram, which you kind of see over here, and just kind of picture an electron living in this shell or an electron living in this shell, and it can hop between them, but it has to live inside of these energy levels. Now what's going to happen is when an electron makes a transition, the energy difference between whatever state it is in and the state that it goes to is going to be equal to Planck's constant multiplied by the frequency, or the color of the light, if you will. And it would kind of make sense that if we had some energy difference right here versus some energy difference right here, well, this one's a little bit bigger, and so if we said E is equal to H times F for this one, technically it's a change in energy level, then this one might be blue because that has lots of energy, this one might be green because there is less energy, and this one right here might be red because there would be less energy still. Now, this particular model of the atom does explain why hydrogen can change the colors of the light that it interacts with, and why it can only put out certain colors. It's because these energy states are discrete. However, it doesn't explain why they have to live in there, and we'll talk about the wave nature of electrons to explain that. But something else that we kind of know is if we go ahead and we take a look at the atomic spectra that comes off of these things, what we kind of see is we're going to start off with lines, and we might have a line in the red region, and this would be hydrogen. We always talk about that one because it's the easiest. But then we might see some lines in the violet, and then we might see lines in the ultraviolet, and so on and so forth. However, as the spacing between the lines is kind of important, and it's going to become closer and closer together. So as we get into the UV, you can kind of see these spectral lines get closer and closer and closer, and they do seem to merge a little bit. Now, a fella by the name of Balmer came along, and he came up with a mathematical formula that kind of predicted the energy levels for these things, but he never explained why these energy levels worked. What he said was the nth level energy level of hydrogen is going to be negative 21.8 joules divided by n squared, where n is the quantum number, and then the ground state n would be equal to 1, and then it could be equal to 2, and then 3, and 4, and so on and so forth. And these are kind of the orbits as we talk about larger and larger and larger orbits. I mentioned this earlier, but fellows by the name of Ritz and Rydberg came up with the Ritz-Rydberg, or the Ritz combination formula, and what they said was if you added the sum of frequencies from two lines together, very often it's going to equal a third line. That kind of makes sense because the energy levels would also add, and we have our good friend E is equal to H times F, so if the frequencies add up, the energies ought to as well. So what Niels Bohr kind of did was he put all these pieces together, and he said these stationary states are going to be states of fixed energy, and we're going to have one here, and one here, and those are the discrete orbits that I've talked about. The energy can be described by Balmer's formula, and when electrons make this quantum jump from one energy state to the other one, so that one down to this one, it's going to emit a certain color. The exact color is going to depend on the energy difference, so E is equal to H times F. So let's kind of come back to my little simulation here, and here we have the Bohr model, and you can see the electron, and it gets excited by certain colors, and it emits certain colors, but only certain colors, very discrete colors. And if we come down here to our spectrometer, that's kind of what colors are emitted. You can kind of see we have some in the far UV, we're going to have some in the red, and there may be some colors that start to appear in here. When this thing absorbs a certain color, it's going to make a certain jump. When it emits a certain color, it's going to make another jump. And it doesn't need to jump successively. It can jump from n is equal to 2 to n is equal to 4, and then back down to 3, and then back down to 1, and so on and so forth. One thing I will note about this particular simulation is that these things are not equally spaced as this simulation implies. Actually, they get closer and closer together, which also explains why the frequencies get closer and closer together, because these circles tend to band together. And actually, you'll see that in the lab that you're going to do. So let's just get a little bit of practice here calculating one of these guys, and please make sure you can do this. You're definitely going to see this on the homeworks and probably the quiz, and definitely on the test. So suppose we had an energy level diagram that kind of looks like this, and you'll also see this in the lab, by the way. What is the wavelength of a photon that's going to follow path C? So here we're going to have an electron, and technically it's an electron that's going to emit the photon. It's going to follow path C. So what we can do is we can take the energy level difference, and that's going to be the energy level from path number, or from the third energy level down to this one right over here. And the change in energy is actually going to be probably 19 times 10 to the negative 19th joules. Now, I do want to mention this pesky little negative sign that's kind of hanging out right here. When we talk about energy level diagrams, we typically define 0 to be the electron being really, really, really far away from the nucleus, and then it needs to essentially fall down a well. And so this energy state right here would technically be more negative than this one right here, which would be more negative than this one right here, and outside would be 0. So that's kind of that pesky little negative sign that is hanging out right over there. And this is going to be equal to Planck's constant multiplied by frequency. So we could say that the frequency is going to be equal to that energy difference divided by Planck's constant. So that's going to be 19 times 10 to the negative 19th joules divided by Planck's constant, which is 6.6 times 10 to the negative 34th. And what you're going to get is you're going to find out that the frequency is going to be 2.87 times 10 to the 15th hertz. Now, I'm actually looking for the wavelength, so we need to come up to our good friend, speed is equal to wavelength multiplied by frequency. And then we could say that the wavelength must be equal to the speed of light divided by the frequency. So remember, the speed of light is 3 times 10 to the 8th meters per second. Divide that guy by your frequency, and you type all that into your calculator, and you're going to get 1.04 times 10 to the negative 7th meters. And if you were to recall that 10 to the negative 9th meters is actually equal to 1 nanometer, then this would be 104 nanometers. Recall that visible light is going to range from 400 to 700 nanometers. This is less than the violet light that we could see, so this is actually going to be in the UV spectrum. So that's why this guy is kind of blue. I highly encourage you to make sure you can calculate this guy and prove to yourself that these guys would be in the red and in the green. Now, there are two teeny tiny problems with Bohr's model of the atom. The first question is the age-old question, why? Why do electrons have to live in these discrete orbits? And the Bohr model has no explanation whatsoever for that. Another problem with it is Bohr's model has the electron essentially orbiting the positively charged nucleus. But we know that if we have a charge, and that charge is wiggling, that a wiggling charge is going to put off electromagnetic radiation. And if something puts off electromagnetic radiation, the problem is it's losing energy, because that energy has to come from somewhere. So Bohr's model of the atom should have the electrons spiral down and then bang into the nucleus. But that's not what happens. Now, before we talk about why that happens, let's go back and take a look at the simulation of this. Before I do that, I do want to point out I've let the spectrometer run for a while, and you can see for this hydrogen atom, we're going to put off very specific colors. Some reds, some cyans, some blues, and some violets. But now I'm going to go over here to the classic solar system, and as I said, the electron should just spiral in and then kaboom. But Bohr's model doesn't explain why that happens, and it also doesn't explain why certain energy levels exist.